Okay, in this video, I will show you guys two really cool things. The first thing is called the Newton's method, and the second thing is called the omega constant. And if you guys want to see more cool things in math, be sure you guys go check out Brilliant.org. I also want to thank them for sponsoring this video for today. Let's begin by talking about the Newton's method first. The idea is that suppose we're looking for the zero of the function, and let's say the function looks like this. Well, as we all know, it's not so easy to solve for zero every single time. In such a situation, let's use Newton's method to get a good approximation. And this is how it works. First, let's recall back from Calc 1. One of the first things that we did in Calc 1 is the equation of tangent lines, right? And we are going to be using that idea to the finest in this method. And here is the idea. We are going to start by just take a guess. It has to be an educated guess, of course, right? And sometimes it also depends on luck. And I will explain more of that later on. But anyway, suppose I want to pick initial guess. I will just call that to be x0 or x0. And let's say it's right here, and then I plug it into the function, and I end up to a point, let's say right here. So this is x0. And as you can see, this is not the zero of the function, of course, but we do get the y value f of x0 after I plug in x0 into the function. Okay? And you see, this right here, it's kind of close to the zero of the function. Okay, but it's not quite. Here's the idea. It's hard to solve for a function most of the time, but it's easy to solve a linear equation, right? So the idea is that let's go ahead and draw the tangent line to this point. Let's see, how does my tangent line look like? So let's say it looks like that. This right here is just an equation of a line. Y is equal to mx plus b. We can let y equal to 0 and then solve for x from there, right? And that's pretty easy to do. Well, let's find the equation of the tangent line right here first. Remember, this line has a slope derivative of the f at x0. So let me put this down. The slope of this line is just f prime of x0. And now we have the point and also the slope. Let's use the point-slope form of the line. I will write this down for you guys first. We have y minus the initial y value, which is this. I will write it down as f of x0. And then this is equal to the slope, which is the derivative. I will write down f prime of x0. And then we multiply by x minus x1, right? But the x1 is the initial x value that we have, which is x0 in this case. Let me just put that down. And then from here, the idea is that I'm going to be solving for zero of this line, which is going to be right here, as we can see right over here. And at this particular point, I'm just going to call this x1. And hopefully this distance is getting to the actual zero, because earlier where I'm kind of off, right? You guys can see that I'm kind of off. But hopefully this point right here, it's closer to the actual zero. But anyway, I will just call this x value x1. And what's the y value of this point? It's nicely enough to be just a 0 because we are on the x-axis. So I'm solving for the 0 of this line. Y is 0. I will put that in right here. And then we have minus f of x0. And this is equal to f prime of x0 times this x is the x1 now. And then minus the initial x value that we have. And the idea is that I care about this x1 because I'm trying to use this to get an approximation for the actual zero of the function. Therefore, let me isolate the x1. I can do that easily by dividing this on both sides first. And let me put this down first. I will write down x1 minus x0, and this will be, here I divide this to the other side, so I will have negative f of x0 or x0, and then divided by f prime of x0, like that. And of course, I can just add this on both sides, so I get x1, and this is nicely equal to positive x0, and then we minus f of x0 over f prime of x0. So that's pretty much it. And as you can see though, x1, this new x value, which is supposed to be a better approximation than the original educated guess. it's depending on the original guess, right? Everything is like in terms of x naught. Of course, you have to rely on the function and also its derivative to work that out. Well, what good does this do? Hopefully it's actually better, right? But before we continue, I said we also have to have the luck. One of the limitations of this method is that if I accidentally pick a value, pick an initial x naught, that has derivative equal to 0 right here, then the tangent line is going to be horizontal, namely parallel to the x-axis. This method is not going to work. And as you can see, if the derivative of x naught is 0, we get an undefined expression, it's not going to work. In that case, don't give up. Just pick another guess and then start all over again. And there, in fact, is another limitation of the Newton's method. I'm going to include the Brilliant Star work page for you guys to read over. So I will talk more about that later. But let me just continue so we can come with the formula and this algorithm. Well, how can we do better? Now, I will look at this as my new x value, and then I'm going to plug that into my function. So I will have this point here, and this point is just going to be x1, comma, f of x1. Yeah? I should say, isn't it? And then from here, I'm going to repeat the same process. Hopefully, I'm just going to draw a tangent line like this. And hopefully, this point here, which I'm going to call that to be x2, 0. Hopefully, x2 is really close to the actual 0. And I know my picture is not the best. That's why you should go check out Brilliant.works page because they have much better pictures and also explanation over there as well. Anyway, here is the deal. We pretty much want to find out what x2 is. It's okay. I'm just going to repeat the same process. But hopefully you will see that x2 is actually nothing but just the same process, and you can just repeat this formula, but instead of using x naught, you use x1 minus f of x1 over f prime of x1. So the idea is you get the equation of this blue tangent line, and then you solve for 0, and then you just get that x2, and that's pretty much it. So hopefully you guys will see that you just pretty much do this as many times as we need to, and this process, if we are lucky enough to have a good initial x value, it's going to converge. And I will just write down this for you guys. xn, meaning the nth term of my sequence, is going to be based on xn minus 1, meaning the previous x value, and then we minus f of xn minus 1 over the derivative at the previous x value, and this is pretty much the approach. And of course, I should put on dot, 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 meaning that you just keep on going and keep on doing this. So you can draw plenty of tangent line, you can make a good approximation. So now let me put this in action for you guys. I'm going to use this right here to help me solve the equation x times e to the x, that's equal to 1. And as you can see, I don't really have a good way in terms of elementary functions to isolate the x from this equation. So I would really have to do some approximation. And I'll tell you guys why this is an interesting question. And this is how the Newton's method is going to work. Let me demonstrate that first. So here is the solution. Look at this equation, and this right here, it's meant to be solving for 0 of a function. Well, that's just minus 1 on both sides. So I can look at a function on the left-hand side, and then that's equal to 0. So let me just tell you guys, this is equivalent to say x times e to the x minus 1 to be 0. And from here, I will first define my function to be this part, which is x times e to the x minus 1. And my goal is to find the 0 of this. And here is some technical part I would like to do before we do anything like that. First, I will just tell you guys, notice this function, it's always continuous. So I'll write down f is always continuous. And that's very nice. And it's also always differentiable, by the way, but yeah. But here is the deal. I'm going to plug in 0 into the function f of 0. And you guys will see that this is just 0 times e to the 0 minus 1, which is just -1. And this is less than 0, right? And I will also plug in 1 into this function. And you will see that this is just 1 times e to the first. And this is about 2.71828, etc. And then minus 1, it becomes 1.718, so on. Anyway, I just care about that this right here is actually positive. Now you see the f function right here. The endpoint of the function f, on the left-hand side right here, the left endpoint is less than 0, and then the right endpoint is greater than 0. That means somewhere in between of 0 and 1, we must cross 0, right? So the idea is I will say by, that's called the theorem, that's the intermediate value theorem, f has a 0 on the interval 0 to 1. And the reason I don't want to include the endpoints is because I know the endpoints, they are not 0 already. So I am just going to be using this idea and then just pick a value and then work this out for you guys. And I also meant to make a note that let's do the derivative. That's the f, right? So f prime of x, which is, I need to use the product rule. So I will keep the first function and times the derivative of the second. And then plus the second function, which is e to the x times the derivative of the first. So as you can see here, I have my original function, and here I have my derivative. And now I just have to throw in into the formula, but before anything else, I would like to have an initial guess, right? So I will just say, let x naught, let's pick 0. Even though I know this is not 0, but it's a nice number to work with, right? So I'm just going to repeat that for you guys. We will see x1 is going to be the following. We need the previous x value, which I pick it to be 0, and then I will have to minus. I plug in 0 into the original, which is going to be 0 times e to the 0, and then minus 1. And then divided by, I plug in 0 into this x right here. So it's going to be 0 times e to the 0 plus e to the 0. And we are lucky because this is not 0 on the bottom, so that's good. You can work this out, and you will see this is actually just going to be a positive 1, okay? And then you pretty much do that again. So I'll just put down x2. I will work this out again for you guys. I will use this as my previous x value, so I plug in 1. This right here, we can actually work it out by using a regular scientific calculator. If you want to say, hey, why don't we just use a calculator or graphing software to solve this equation? That's too boring. That's demonstrate the Newton's method. This right here, you can just use a regular scientific calculator to work that out. And I will tell you guys, this is approximately 0.6839. Okay, I have this on the screen, so that's why I'm looking at that. So you pretty much just do that. And then, of course, I will just tell you guys, we are going to continue the process, all right? And then I will just write this down for you guys. x3 is approximately, I'll write down the answers now. The next answer that we get, you plug in this into pretty much this formula. You are going to end up 0.57745. So I'll just put down 5, all right? And then x4, this is approximately 0.567 so I'll just put down 2. And then x5, so that's the 5th time that we're doing it. And this was a pretty good initial guess because you're going to see that the next number I get is 0.56714. Something else after that. I know I put down 5 decimal places because you'll see the next one, x6. If you plug in this into the formula, so you start with this as your x value, and then plug in this into the original, and then plug in this into a derivative, and you divide. you're actually going to get the same thing pretty much, 0.56714. And if you do it again, you're going to get this number back, approximately speaking, okay? And show you guys on the screen, it's pretty much the list of the numbers after 6 times of this iterations. So you can see that this right here is pretty much going to be a really good approximation of the zero of this function. Namely, if you plug in this into x and then times e to that number, you are going to get almost 1, because this is just an approximation. So I will tell you guys the answer to that. I'll just write this down. If you want to have x times e to the x is equal to 1, the answer is approximately that, 0.56714, right? So this is pretty much it, the answer to that original equation. Well, I told you guys in the beginning of this video, I will show you guys 2 really cool things. Hopefully you guys find this fascinating, because this is just brilliant. Because you use just a basic Calc 1 stuff, bunch of tangent lines, and then you were able to do this kind of computation, and you can get a really good approximation to solve for the zero of the function, right? And the second thing I want to tell you guys is the following. This number is actually really, really special. I'm going to call this, well, actually not me, but like other people have called this already. I'll just put down a note right here. When you see this number, 0.56714 and so on. This right here is defined to be the omega. So this right here is the omega, right? So omega constant. So I know a lot of people, well actually everybody should have seen like pi, 3.1415926, so on. E is also, we talked about that earlier, square root 2, 1.414, ln2, 0.693, and so on. And the golden ratio of phi, 1.618. But have you guys seen this omega constant, which is about 0.56714? This number is so cool because when you plug in this omega to here, you actually get 1. And the property of this is that omega, that's actually really hard to write. I haven't wrote like this like in my videos. Yeah, omega times e to the omega power, this right here, it's actually equal to 1. So this is a really beautiful equation. And what's cool thing about this is like a small bonus part. So technically I should say it's really, really cool thing. Because the last thing I want to tell you guys is this right here has something to do with what we call the Lambert W function. So let me just, how many notes do I have already? I don't know. I'll just tell you guys the following, right? So let me introduce you guys the Lambert W function. And that's the idea of the following. Suppose you have the function, I'll just say let f of x to be x times e to the x. And as we mentioned earlier, we cannot really isolate x from this equation. And similarly, we cannot really find an inverse for this function. But it's okay because we're going to define a new function to be the inverse of this function. So when f of x is equal to x times e to the x, then we say that we're going to define w of x, and this is the Lambert W function. We are going to define this to be the inverse of this function. And now let's take a look at this equation again. So earlier we wanted to solve x times e to the x being equal to 1. Well, this part is exactly the f of x that we have. So in another word, we're looking for what x will give me the function right here equals to 1, right? And now, because we actually have an inverse function for this guy, which we call it to be w, we can just go ahead and take w on both sides. And because w is defined to be the inverse of f, therefore they cancel each other out. And I just get x by itself on the left-hand side. And what do we get on the right-hand side? We just get W of 1. So let me just put this down. And now you may be wondering, what is W of 1? Well, this is supposed to be the solution to this equation. And in fact, we did that earlier already. Because the solution to this equation is approximately 0.56714. Therefore, we know W of 1 is approximately the same as this. So if you would like, you can write it down right here. W of 1 is approximately 0.56714. But better yet, this number, we call it to be the omega constant. In another word, W of 1, this right here, is the omega constant. Alright, so this is really cool, and hopefully you guys all like this video. And before we go, I would like to tell you guys to go check out Boolean.work. Boolean.work is an excellent place for you guys to go if you want to learn about how to solve interesting challenging math questions, because it offers a wide range of course in number theory, probability, calculus of course, and the differential equation, and a lot more. You guys can go check them out. You can sign up for a free account today, and then you can also try their problems of the week section. And they also have this community page. You guys can all check that out for the questions that other people post around the world. And I go to their website regularly just to test myself to see if I can solve their questions or not. Sometimes the questions are really hard, but it's okay because we like to think, right? And if you would like to learn about something new, you guys can also check out their wiki page with a lot of interesting resources, great resources as well. And if you're also interested to sign up for the annual premium subscription, be sure to use the link boolean.work/blackpenredpen, because if you're one of the first 200 people to sign up with that link, you can get a 20% off discount to their annual premium subscription, and that will also give you the whole access to all of their courses. And you can start learning today. And once again, thank you guys so much, and as always, that's it.